Hello, welcome to the Life of a Touch talk. My name's Harry Cutts. I'm a software engineer on the Chrome OS platform input team. And in this talk, we're going to look at how touch events get from your fingers on a mouse or touchpad or keyboard through the system into Chromium and your apps. If you've got any questions throughout the talk, then please put them on the Slido and we'll have some time at the end to get through them. But without further ado, let's get started. So in this talk, as I said, we're going to cover the whole stack, but with a couple of exceptions. So we won't talk about the logic that's the same on all platforms. For example, the logic that propagates a click down through the DOM into a particular element or anything. And we also won't talk about UI-focused input code, so input method editors or virtual keyboards. So here's an overview of the stack. On the left here, you can see we've got the input devices themselves, and then the data goes through the Linux kernel, then Chromium, and then finally into web pages and apps. So first, let's look at what a touchpad actually is and what its touch controller does to get your input. Here we've got a diagram of a typical touch screen or touchpad structure. At the top, we have the glass that you put your fingers on. Then in the middle, we have these three electronic layers. Two of these are lines, so the scan lines and the drive lines are basically just wires. And in the middle, we have a dielectric component. And this is a layer that changes its capacitance as a finger gets closer or further away from it. So essentially, we have this grid of capacitors that we can measure by changing which line we drive. So the touch controller will drive each line in turn and then read the resulting capacitance on each of the sense lines. And that will give it a heat map of touches across the whole display or touchpad, which we will get to in a moment. Then at the bottom, we have, if it's a touchpad, we just have some casing. If it's a touch screen, we have a display, and then touchpads will have the whole assembly on top of a dome switch, typically, so that you get the nice satisfying click down when you apply pressure. So that heat map that we talked about is acquired about 60 to 100 times a second, so at quite high speed, but it's very low resolution. Typically, those wires are only 1 every 5 millimeters or so. So you can see these are 2 fingers that you can see on the left, and we've only got maybe 6 pixels or 9 pixels each. So this is not nearly high resolution enough. So the touch controller then does something we call centroiding, and it finds the normally Gaussians that match these clumps best, and gives us, for each finger, it ends up giving us some position, size, both width and height, and ideally it also gives us a rotation. So you can see this finger down here is actually rotated a little bit, and that can help us in some of the filtering we do later. This animation shows the centroiding in action, and you can see that the center of the finger, represented by the dot in the middle, has a much better resolution than the heat map overall, because even though we've got 1 line every 5 millimeters here, we're getting nice smooth movement in the centroid. Okay, so now we have the touch controller knowing where the fingers are, but it needs to be able to communicate that to the CPU. And to do that, we need a protocol. Many vendors have their own protocols for this, which are quite simple, but they can't be understood without a special driver. But increasingly, accessories are talking a protocol called HID. HID stands for Human Interface Device. As that name suggests, it's pretty generic. Although I'm using touchpads and touch screens mostly here, it also applies to mice, keyboards, gamepads, graphics tablets, all sorts of things, and a bunch of stuff that you probably wouldn't think of as a human input device in many cases. Although originally it was made for USB, It's now being used in Bluetooth and also over I2C, which is the bus protocol that's commonly used within a Chromebook. And in HID, each device has a descriptor. A descriptor is a little like a C-struct definition in that it describes a way that various different data fields are serialized. But as well as that, it also has some sort of semantic tagging, which tells the host how to interpret the data without having a special driver. So here's an example of a descriptor. This is a descriptor for a very basic 3-button mouse with no wheel. You can see we have at the top a usage that tells us this is a mouse. And then further in, these usages describe buttons. And they don't just say they're buttons, they also say that it's 1 bit per button, that there are 3 of them, and that that single bit should be interpreted as a number between 0 and 1. And then further down, we've got something similar for the X and Y axes. So usage X and Y, and these have meanings. So there's a table of all of the different usage codes and how they should be interpreted. And again, minimum -127 up to 127, and then here 8 bits each, and there are 2 of them. So now we have a way to communicate this data. We next are looking at the Linux kernel, which is the first piece of software on the CPU that handles our events. Obviously, the Linux kernel is a pretty big, complicated thing, but here we're most interested in what drivers are involved in looking at our input. So first, we'll have the transport driver. That will be specific to the way that the device is connected. So there's a USB driver, one for I2C. Bluetooth is a little special because there's a component called Bluesy that takes the traffic first and then puts it into the kernel. But in any case, the transport driver just gives us a set of bytes that were transmitted, and then that goes into the HID driver, assuming that it's a HID device. So the HID driver will do as much as it can to interpret the packet, but can only do so much because there's only so much in the standard. So then there could be a vendor-specific driver that's provided, and that vendor driver can take the things that the HID driver wasn't able to do and add them to the report. So for example, many mice with high resolution scroll wheels don't actually use the HID standard way of doing that, and they just have a vendor-specific extension. And so in that case, the HID driver will still be able to unpack the X and Y in the buttons, and then the vendor-specific driver will unpack high-resolution scroll data. Or if the device isn't HID at all, then the vendor driver will just read directly from the transport and do its stuff from there. Whichever is the case, we don't want to be thinking about this past the kernel. We just want a standard representation of any input that comes in. So the kernel has a protocol called evdev, or evdev. evdev is a little different from HID in that instead of sending everything every time, it only tells you what's changed. So for example, if I move the scroll wheel on a mouse, then I will get a bunch of reports that only contain the scroll wheel position. They won't give X or Y changes. So it does give us a list of axes and buttons, like you can see here. So again, we have this is a 5-button mouse this time with the X and Y coordinates and vertical and horizontal scroll wheels. All of these events then come through some nodes, some file system nodes in dev input. And any program that can read those nodes can look at the input events. And one of these programs is a handy little one called evtest. evtest gives us a list of all the devices connected and then lets us see any of the output coming from them. So in this case, this is a mouse, but it could also be keyboard, trackpad, and actually a bunch of things that aren't really what you'd think of as input devices. So for example, a headphone jack probably has a switch in it that tells you whether something's plugged in, and that's available in evtest. So here's some example output, and you can see we have a timestamp for each event, as well as the axis code and type. So here we've got the X and Y axes moving with these values. And you'll also see these SYN report lines. Oh. And these SYN report lines tell you where the boundaries are between the reports. So you can see the timestamp changes after this one. So typically when you're processing your VDEV, you just buffer up all of the events that you're receiving until you see SYN report, and then you process them in one go. So now we have a way to communicate the kernel's results into user space. And if you're familiar with other Linux-based operating systems, you might be expecting me to talk about X or Wayland at this point as a display server, but no. On Chromium OS, we have our own display server called Ozone, and it lives inside Chromium itself in the same binary. So Ozone reads these input nodes directly, and then it creates something called an event converter for each device. An event converter is specific to a device type. So there's one for touchscreens, or there's one for touchpads and mice as well, and so on. And its job is to convert these evdev events into the browser's internal representation of events. For a mouse, that might be quite simple, but for touchpads and touchscreens, that means you have to do gesture detection, which brings us to the gestures library. So the gestures library forms the core of the event converter for touchpads, mice, and multi-touch mice. And it takes in those finger locations and gives us a gesture structure. So for example, if I have my 2 fingers on the pad, like so, and I move them in and out, then I am giving it finger locations, and the gestures library will output a pinch gesture structure with magnitude telling the rest of Chrome how much I'm moving my fingers. But we can't just do that. We also need to filter the data to improve quality. So there are various issues that we get coming from touchpads. It could be as simple as a palm coming up and touching the pad, or it could be that a pad takes a thumb, which is quite a large touch, to be actually 2 touches that are separate, even though they're not. There's also an annoying thing where you press down on a pad with a button and your cursor wiggles a bit because you're moving around, and so we have to account for that. And so we do various filters like this to improve the quality of the data before we do gesture detection. And a lot of this varies per device. So some touchpads are better at, say, detecting thumbs than others, and so we adjust the sensitivities of our various filters to make the touchpad on a particular Chromebook work nicely. And we have a set of configuration files that the gesture library then applies to its operations. So at this point, we have the events into Chromium, and we've reached that cross-platform code that I mentioned that would then send them on to web pages and the rest of the Chromium OS UI. But as you might have noticed, these days we do more than just web pages on Chromium OS. So we want to also send these events to Linux and Android apps. And this is where Wayland does come in. So Wayland, for those who aren't familiar, is a protocol for Linux apps, traditional Linux GUI apps, to talk to the compositor with. And so the app will send things like frames that need to be rendered in its window and so on. And in return, Wayland sends input events to the app. It was developed as a replacement for X11 in the wider Linux desktop ecosystem, and we've now adopted it for our Linux and Android apps. So we have a component in Chromium called Exo, or sometimes you'll hear it called Exosphere, and it is an adapter essentially that allows the Chromium display server to be used over Wayland. And so for our purposes, it takes input events and makes sure to dispatch them to the appropriate app's window. If that's a Linux app, then it's running in a VM, Crossgenie, and there is a component within the VM called Sommelier, which the apps running in the VM think of as a Wayland compositor, although really it's just delegating most of its work to XO. And so our input events go from XO and into Sommelier, which then send them on to the app's window. A lot of Linux apps don't actually support Wayland yet, so there's an adapter library called xWayland, and that translates the Wayland events into X for those apps to understand. For Android apps, it's a little more complicated because Android apps don't natively understand Wayland. So we have a component inside Arc++, the container that the apps run in, and that translates from Wayland events into Android input events. And the couple of catches here are that Android apps often have particular ways they want to handle touches. So for example, if I'm in a video game, maybe it has one of those virtual thumbstick things on the screen, and it doesn't want to take any gestures in, it just wants to know where the fingers are. So for touchscreens, we actually turn off gesture detection entirely for Android apps, and we just pass them the finger locations. Conversely, barely any Android apps have touchpad compatibility. So for that, we have to do more tweaks. We can send the mouse events for some things, but for example, the pinch to zoom gesture that I gave an example of earlier doesn't really have an equivalent in terms of a mouse, and we can't simulate it. We can't just make it directly a touchscreen event, because on a touchscreen it would have a center, whereas on a touchpad it doesn't have a center coordinate relative to the screen. So for things like that, we actually pretend that there are two touchscreen fingers on the app moving in and out, even though there aren't, but that makes those gestures work. So now we've reached the end of the input stack. So to recap, we covered the touch devices centroiding and how they work, the HID protocol that transmits the data from the devices to the kernel, how the kernel then interprets the events and runs it through the drivers, how it sends it over evdev, how Chrome then converts that and recognizes gestures, and finally, how we use Wayland to send the events on to the apps. There are a number of good resources for this, and you might not be able to click the links in this slide right now, but if you search for these titles, then they should be the top result. Partly, we have the input stack documentation for Chromium OS, which I based most of this talk on. That has a lot of the same content, but it goes into a lot more detail. And it also goes through a lot more tools for looking at various stages of the stack. So like EV tests, there's also a tool for viewing HID traffic as it goes into the kernel, and for looking at Wayland traffic in the VMs. Frank Zhao has written a great tutorial on HID descriptors, which is a very good starting point if you're wanting to learn about the protocol in particular. There are also some usage tables around available for free. The kernel has evdev documentation, which is also thorough and gives you a good introduction, especially to how multiple fingers are handled over evdev. And if you're interested in Wayland, then there is a Wayland book available for free online, which is a useful starting point. But maintaining this stack isn't everything that my team does. We also have a variety of other responsibilities to keep us busy. One of those is setting specifications for the input devices that we allow to be included in Chromebooks. We also work to make sure that peripherals are compatible with Chromebooks, and we set standards for them through the Works with Chromebook program, which is a certification badge that peripheral vendors can acquire. We manage firmware updates for input devices, making sure those are smooth and that they don't break your device if you suddenly lose power in the middle of one, for example. We do a lot of work with the Universal Stylus Initiative, and that's a project where we're aiming to standardize the protocol that connects a stylus with the touch controller, with the objective of having styluses that can be used with any Chromebook and hopefully many other devices as well, rather than having users have to think about, oh, well, I bought this stylus and will it work with this Chromebook and that Chromebook, or so on and so forth. We also work to do robotic testing of touchscreens, which helps us to get qualitative and quantitative metrics on how well a touchscreen performs before it is certified to go into Chromebooks. And we're constantly experimenting with new input ideas for future products. So that's the end of my talk. Thank you for listening. And let's now see if we have any questions. Let's see. And I can't quite read this. Let me bring this up. Chromium B. What is the latency difference in the event feed to Linux apps versus Arc++? That's an interesting question. I think between Linux apps and Arc++ is probably reasonably similar. The main issues there are hops between VMs and the general running of the Chromebook. So probably there's more of a difference between Linux apps and the native Chromium running on the device. But I don't think there's particularly much difference between those two. Okay, and apparently that's all the questions. So thank you for watching, and I hope you've enjoyed the talk. And feel free to obviously reach out with any questions. Yep.